Okay. So we have three different balances, and we're going to interpret what these balances say. Okay, so we have three different balances, and the idea of a balance means that they're equal on both sides. So the balances, there's one back there, you guys see the balance back there, the old, you put weights on one side and you put an object away on the other, and you just keep adding and subtracting weights until they're equal. And then you look at the weights that are on there and you add them all up. You got a 10, a 15, a 20, and then it balances out, so you say the total is like, whatever that totals up to be is going to be the weight of the object. So this is balanced. Everybody can see that. Okay, it has the same number of whatever you want to call these objects that are on both sides are equal. Over here, it's pretty evident that this needs one more to get balanced. And on this side, it's the opposite. So this is balanced. We're counting, and we can see that this is the same object, and that it just makes sense that when we look at these balances, that's kind of the way they would move. And then we'd have to add another one to this side, then it'd be equal, right? Over here, I'd have to add another one and be equal. And that's what we're doing on balancing. So the first sheet we're going to kind of go through has 4 quadrants. Okay, in the middle of those quadrants is, what's in the middle?
Balanced equations.
Balanced equations, right in here, right? Okay, balanced equation. So in the upper left quadrant, we have why should equations be balanced? So let me give you some information about an equation first so that you can really focus in what an equation is. So here is an equation. On this, you can write this down later, but here's an equation. It's called a chemical equation. What's on the left? What's the left side's called what? So on a chemical equation, these H2 and O2, what are those called? Reactants. And then these are products. So this reaction says if you take, I'll do this one for you later, maybe later this week. Okay, so we take hydrogen and oxygen, react them, then this reaction says you're always going to get water out. Okay, when they go together, you're going to get H2O out. So you got reactants and products, and this is an equation. So the first statement, why should equations be balanced? Now I want you to look at that equation and tell me, is it balanced? So some of you are like, I don't know really what to look at to know it's balanced. So the first thing you look at is you look at how many atoms you have on the left versus the right, and what kind of you have on the left and right. So on the left side, how many hydrogens do you have?
2.
There's 2.
Yeah.
So I could do a drawing, and that drawing would show 2 hydrogens, and that's 2 hydrogens. And then we also have 2 oxygen. Oxygen atom's a little bit bigger. Okay, and then we have an H2O. So, if we had a balance, would this balance be even?
No.
No. Wouldn't be even. Because what's wrong?
We need another oxygen on the product side.
Yep. So what's wrong on the product side, we're only showing one oxygen on the reactant side, we're showing two. So the left side would be heavier. And it wouldn't balance out. Now, we know that all oxygen atoms weigh the same. So we know that on the left side, we got one more oxygen atom, and so it's going to be heavier, and it's going to weigh down on that side. So it's not balanced. So why should equations be balanced? So we got this law. The law is the law of conservation of mass. And it says the products and the reactants have to equal in weight. And this one doesn't equal in weight. Okay? So that's what you need to put in that side. Why should equations be balanced? Because we need to prove the law of conservation of mass. You can just put law of conservation of mass in that quadrant. So right in this quadrant, put law of conservation of mass. It does not explain why they are equal. It just says if you're going to show law of conservation of mass, the masses they're always going to equal. Every time you do a lab, every time you do a reaction, every time you melt something or freeze something, the weight does not change if you keep all the molecules there that are originally there. Not going to change. So law of conservation of mass in all reactions are constant. They don't change. All right. So when we take a look at the right side, what is conserved in a balanced equation? So conserved or kept the same. So let's take a look at this, and we're going to introduce the bottom left-hand one. What are coefficients, and why are they important in equations? So there's no coefficients in this equation right now. Now I'm going to put coefficients in there, and then we're going to adjust the molecules down below. So I'm going to put these numbers, they're whole numbers. That's what a coefficient is. It's a whole number that you put in front of a reactant or product. So in the future, if I ask you on a test, or I ask you to write coefficients in, they are the numbers in front. So if I wrote 2 in front of that, how's that going to adjust to this one down here? So if I put a H2 in front, how does this change? Or does it change? What do you think? What do you think the 2 represents? 2 of these molecules, right? It tells you how many molecules you have. So I have to draw another molecule. Where else do I have to draw another molecule?
On the product side.
H2O. Now, would that balance be equal?
No.
And how do you know it's
Oh,
equal?
yeah, it would.
And like 2 of oxygen. On the other side of products, there's 2.
Yep.
And on the other side of oxygen, there's 2.
Yep.
And on the other side, there's 4 hydrogens, and on the other side, there's 4.
Right. So you guys can count these, but you don't want to do the drawing every time. You want to get to the point to do like I did, where you just put numbers in front and can count them by putting numbers in front. Okay? But sometimes you get a really tough one to do. I don't hold it against you or anything. That if you do drawings and you do them the right way, you're going to be able to balance every one. Because eventually, trial and error, you're going to be able to figure it out. Okay? So what do coefficients do? It says, what are coefficients? Coefficients are numbers in front of the reactants and products in a chemical equation. So they're the numbers you write in front of formulas in an equation. That's what they are. Why are they important? So why is it important for us to write numbers in front? What do they do for us? By putting the numbers in front without doing the drawings, what do they do for us?
Do they like check to make sure that they are Or aren't balanced.
Right. So you can add numbers so that you can eventually balance how many atoms you have left and right. So what coefficients are important in doing in equations, they allow you to balance the reaction when it's not balanced. It allows you to add more reactants and products so that you can get it balanced. That's what coefficients do. Okay? So that's what you would put down in that bottom left-hand corner. What is conserved? So when we had these drawn out, what is conserved? Tell me something that's conserved. That's a really easy statement to recognize. What is conserved when we take a look at a balanced reaction? What's conserved? Mass, yeah. So you can write that down because I'm gonna give the weights for everything. 4 grams, 32 grams, 36 grams. Everybody knows how I came up with 4 grams, right? Because each one of these is 1 gram, so that's 4 grams. Oxygen, each one's 16, that's 32. And then when you take water, you got 2 hydrogen and 1 oxygen, that's 18 grams, and you got 2 of them, that would be 36. So it says down there, what is conserved in a balanced equation? It is mass and what else? So if we don't have mass, how do we know it's conserving? We have the what? Same number of atoms on both sides of the reaction. The number of atoms and type of atoms are identical on both sides. Because you're not weighing them out. All you're doing is counting. So there's 2 ways you can look at it. You can look, if you're given the weights, they should equal. If you're just given the actual formulas, you know you got to count them out. Okay? And then for the bottom portion, if you just want to go ahead and write this out, this is kind of shows the macroscopic, which is these individual drawings. And it shows the levels with the numbers in front. These are the symbolic ways of showing H2 and O2. So if you write that whole thing out, you have everything covered on that part. Now this is kind of your notes for coefficients, why something has to be balanced because of the law of conservation of mass, how you can show reaction being balanced by counting or by putting numbers in front or buying weights. Okay? What we're going to do is do a little practice balancing equations. And we're going to start by drawing first, and then a lot of you will not ever draw anymore unless you're asked to do it on a question. And then you'll have to draw. And that's the part that students struggle with, is the drawing after we've been away from it for a while. So the next sheet we're going to look at is the one, it's the second sheet, and it has at the top Na2O, H2O, and NaOH. So this is what we're going to have you do. We're going to have you do something similar to this up here. You're going to draw 3 drawings underneath. And I will help you with the first drawing, since some of you don't remember how to draw these. So I'm going to help you with the first one. And I'm going to have you do the next 2 yourself. So there's the first drawing. You do the next 2 drawings. And we just need one of everything to begin with. So do 3 drawings. You guys are in art, now you can show your artistic. This is a good way to visualize the molecule, and sometimes students have a difficult times transitioning and counting and using the subscripts and the coefficients in front in which to do the counts, count everything up. So it's something that you could go back to if you really are struggling in balancing an equation. But we'll start off with this method. So this is what I'd like you to do. I want you to do how many drawings you have to make to where the atoms on the left side and the atoms on the right side equal. The only thing you got to make sure you do, if you do a drawing, you have to draw the identical compound underneath the one that's already drawn. Keep drawing until they're equal, both sides. So go ahead, kind of look at it, kind of see where you need more atoms, okay? And then do the number of drawings you need, and then stop. So go ahead and draw those out. I think each and every one of you. See, the trouble is students want to manipulate these and not draw them exactly the same. If the drawing's right, you've got to, by putting a number in front, basically you're just adding on an additional number, a molecule or an atom, depending upon what you're drawing. So are they equal?
Yes.
So when I count sodium, there's 2. I count hydrogen, there's 2. And I count oxygen, there's 2, right? So all I do is put a number of 2 in front of that, and that's my coefficient, right? Now, I might have you do this a little bit later, because I think everybody can figure out molar weights and that. Do they add up? The weights? They do. Na2 is 23 times 2 is 46, plus 16 is 62. Water is 18. And Na is 23, plus 1 is 24, plus 16 is 40. I've got 2 of them, that's 80 grams. So they're always going to equal out, the weights. And it's a good thing we don't have to do their weights all the time, because all we have to do is count. Now, number 2 is a little trickier. See if you can do number 2. That's a little bit more time and effort needs to go into that one. So go ahead and see if you can do number 2. Keep drawing until you get them equal. Now this would be a tough one to do. I have a lot of students that would get this wrong on the test if they do get this one a lot on the test wrong if we have a test at the end of this unit. But if you draw them out, it makes it pretty easy. So if you get one that looks like it should be easier than it actually is, you're doing it, then you might do some drawings to help yourself out. You don't want to do that on too many, because it takes time to do drawings and you only have so long to do a test when you've got like 15 of these to balance. So, but it's kind of a good start to kind of see the connection between the coefficient and the drawings. We eventually do not want to draw anymore. You want to get to the point where you're not drawing anymore. Okay? That you're just counting in your head. You're like, oh, that number is this many atoms. On the right side, I have this number of atoms. I get them to equal. Kind of like charges. This one's a +2. This one's a -3. I got to have 3 of these and 2 of these to balance out the charge. It'd be the same idea. So in your drawings, did you have any more K's that you drew? Okay. Now, let's just go in transition. I think most of you would have, in transition, you would have saw K was in equal. So you'd said, no, I'm not going to do another drawing of K, because there's no reason to do that. And then you look at O, and guess what? They're the same. But the H's, I have 3 over there. And over here I have 2. So I need more over here, so I'm going to do another drawing of these. So I do another drawing of that. But my hydrogens still don't match up. Over here I've got 3, and over here I've got 4. And the oxygens don't match up either. So what would be my next drawing I'd want to do? KOH. So I'm going to do another KOH. And then I look at my Ks. Well, let's look at O's. Do the O's match up? How about the hydrogens? How about the K's? They don't. So I do another K, right? Now, is it balanced? Yeah. So we just transition. We put 2, 2, 2. And so the drawings can really help you balance it, but you want to get to where... I'm going to have you do one more drawing, and that's the last one I'm going to have you do. I'm not going to have you do any more drawing after that unless you want to. Do number 4. Do number 4. Now this one is, you're going to get frustrated with the drawings, number 4. But, yeah, just try it and see. You have to draw a little bit smaller on number 4. This is why you don't like to, this is one where you would not want to draw. The 2 prior ones would have been okay. And when you get to this one, it's like, oh no. Why do we have to draw this one out? I could have did this in my head. Where do I start? And so most of you started like, okay, that side has 2 H's, this side has 1 H. I'm just going to get the H's equal. And that's the same thing that you do when you put numbers in front. You just say, there's 2 H's there, there's 1 H here, I'm going to put a 2 in front. Well, the H is balanced, but the chlorines don't. So then you go, wait a second, that's not going to work out. I need another chlorine. So I'm going to put another H here and Cl. When you do that, then you change your number in front and you say, well, that's not a 2. That's a 3. But then what's wrong? The hydrogens don't match up. So you say, well, I'm going to put another H here. And so that's what you put a number in front. And you go, hey, I'm going to put another 2 there. And the H is, wait a second. That's 4 and that's 3. I'm going to put another HCl here. And now, when you do this, the numbers in front, you probably won't do it like we're doing the drawings, okay? Because they won't make sense. But right now I have 4 there. Okay, what? I need 2 more. The H's work. The chlorines are off. So I need another one of these, right? So then I got 6 chlorines there. So I put a 2 here. Now I have to have 2 more of these. So So then this becomes 6. Well, over here I have 6, and I got 4 hydrogens. I got to need another one of these, right? So then this becomes 3.
But you need another.
Isn't the aluminum supposed to be 2?
Oh, so there's 2 aluminums there. I need 2 here. So there should be a 2 in front, right? That's balanced. It's a lot of work, isn't it? It's not, and it's
I'm trying to do this every time.
no. So let's do one similar to this that would be kind of similar in pain, trying to do it. And let me find the one that it is. Let's do 2A without doing any drawings on the reverse side. So go on the reverse side, and we're going to do 2A. But we're not going to draw. And all we're going to do is put coefficients in front in a logical, thought out way before we even attack this. Before you even start putting numbers in front, you're going to sit back and you're going to look at what you're given. Okay, so AL's balance. So then you don't even look at AL and you need to look at CL3. If you notice, you've got a 3 subscript and a 2 subscript. What are you going to need to get both of those 2 to where they balance? 6. So what you do is you put numbers in front of both of those to get 6 chlorine. Does that give you 6?
Yep.
Okay, don't worry about aluminum. Now fluorine, what are you going to have to do? So if you got a 2 here and a 3 here, you're going to have to do what with that? Put a 3, get 6, because if you had 3 drawings of that, means 6 total. And you put 2 here, which give you 2 drawings of AlF3, which give you 6 fluorines. They balance. Then you go back to aluminum and look at it. Does it balance? Yeah. Anytime you got 2 subscript, 3 subscript, it's like having a +2 and -3 or a +3 -2. You have to get them to 6. Does that make sense?
Yeah.
I did not do any drawing. I just counted in my head. Okay? Let me have you do one more. And then let's do this one without drawing and see if you can get it. And that's number 5 on the same side we started out with. C3H8 plus O2 gives you CO2 plus H2O. Do that one. Put numbers in front to balance it. You have 3 elements, carbon, hydrogen, and oxygen. If you want to draw them, you can. If you're saying there's no way I can do this, I can't figure it out, see if you can draw them. The thing you guys got to do, here's what you need to keep away from. So when you do this one, you got to keep away from oxygen to the very end. See, why do I want to kind of keep away from oxygen? Any ideas? What's different about oxygen compared to carbon and hydrogen? It's twice on this side. You got 2 different locations with oxygen you got to count into. So you kind of got multiple variables there with oxygen sites. So hit H first, then hit carbon, then H, and then go to oxygen last. So there's certain little helpful hints. Don't ever balance elements that occur in multiple locations on one side of the reaction. Do not balance those and leave those to the very end. The reason we're doing this, in the future we're going to do chemical reactions and we have to know those relationships. In welding, some of you guys that take welding, there's a certain ratio of oxygen to acetylene that you have to keep to get where you don't waste one or the other. And where you get the hottest flame without waste. And we'll do that at the very last. Okay? This is acetylene. We'll come back to that. But this is acetylene. C2H2 is acetylene. Here's oxygen. You always produce CO2 and water. It's called a combustion reaction. So, in acetylene, these ratios have to be, they're not going to be 1-to-1. If they're 1-to-1, what you're going to do is you're going to waste one of the two. And they're not going to burn. And you're going to waste them, and that's money. Okay? And plus, you're probably not going to have a hot flame, and you're going to have overly rich in one or the other. Okay? So that's why balancing has to happen. So you guys put a 3 in front of this one, right? Because of that 3. And then you realize you had 8 there, and this coefficient's a multiplier, so you put a 4 in front of that to get your 8 hydrogens, right? You did that? Then you realize I've got locations of oxygen in 2 places, so I need to make sure I count them all. So here you have 6, and here you have how many? 4. You everybody see why you have 4? If I dry that out 4 times, that means I draw oxygen 4 times in that molecule. And then when I draw this one out 3 times, that means I've got oxygen drawn where I have 6 of them. So that's a total of 10. So what number needs to go in front of that to get 10? 5. Okay, and I didn't do any drawing. Okay, and then this is that's the last one I want you to do. I was going to give you something else to do. Write that out somewhere on that sheet. Why don't you do it under the Al plus O2 gives you Al2O3. You can just write, you got enough space to write that underneath the reverse side. It has 2A through E. Just write it under 1A. And I want you to balance that. See if you can balance it. That would be a pretty tough one to do on a test. Sometimes you might have to draw it out and if you're not getting it. And you do have to go and erase your numbers at times. I mean, sometimes you get one. Just because you put a number there doesn't mean that's going to stay that number, that coefficient. So you may have to adjust from time to time. So this is the ratio when you use acetylene. This is the ratio that you would want to combine those two from the tanks, from the oxygen and the acetylene tank. And don't they do that with flow? Don't they adjust the flow of the oxygen and acetylene? You guys welders? Do they adjust the flow? Right. You have places where you can have more volume coming out and less volume coming out for acetylene torch when they combine or not? Or am I thinking something different?
Torch too.
What's that?
And the torch too.
Right. But you have two different.
Yeah.
Right. You have two different ways to adjust your oxygen and your acetylene, right? Okay. And then when you adjust it, you can probably tell when it's the hottest part, when it's right. Okay. And So it just, by doing it, it's adjusting the ratio. You guys think you got it? Okay. Okay, so the way I would do it, I'm keeping away from oxygen. Here's another key. Okay, here's another key. What number I put in front of it, what kind of a number I'm always going to generate when I have a 2 here. What kind of number will I always generate, what type of number will I always generate when I put numbers in front? Yeah, they're positive, yeah. But what kind of number? So if I put a 2 there, I get a 4. If I put a 3 there, I get a 6. I put a 4, I get a 5. What kind of numbers are those I'm generating? They're also even. They're all even. This side's not even. See, the oxygen's in that side's not ever. So I got to get that side when I get to oxygen. I got to get it even. So I'm going to put a 2 here to balance my carbons. Boom, got it. Hydrogen's balanced. Boom. Oxygens are odd. Even. So guess what? This is the easiest way to do this. Okay? The easiest way to make an odd side even is to double everything. So, how many do I have here? 2? I'm going to make it 4. And what do I need to do with this one? Make it 2. Now, I'm going to go back to my carbon. How many do I have here? What do I have to put in front of this then? A 2. Now I'm going to look at the hydrogen. Is it balanced? Okay. Now how many oxygens do I have on that side? 10. I have 8 and 2 is. So what do I need to put here? Now that's a tough one. So when you do a settling torch, it has to be 2 to 5 ratio. You have to have 5. You have to have 2.5 times the amount of oxygen to 1 acetylene molecule to get it to work perfect. Okay. All right. You guys can put those away. We will practice some of those tomorrow.